Can you see the screen? Hello?
Yes,
Can you?
sir.
Okay, all right. Just hold on. Okay, yeah. So it is just the continuation of the same topic that we have been talking about. That it's a normal distribution, and the other day I started. However, I didn't speak about what are the other different types of distribution that are available. Okay, and how this normal distribution is basically it is connected to probability. Okay, that we'll be talking about today. So mainly we'll be looking into the probability and the area and normal distribution. So I'll also give some website link in which you will see the examples also. So if you work out, that will make the concept more clearer. Okay. By the way, I have one question that will ask in the middle, not now. Uh, okay. Now, what is distribution? Basically, distribution is that it gives the probability associated with each possible outcome. Okay. So, if I say it is what is the probability, that's what basically it gives a basically probability. If I say that, okay, fine, there are if I just toss one coin, what is the probability and how the okay. So and a summation of all probability, that it is going to be one. These are all your basic idea. Uh, so and distribution of continuous data are characterized by probability density function. Uh, okay, so that if you just integrate from minus infinity to plus infinity, fx dx is going to be 1. And now there are several types of distribution available. Okay, already we had frequency distribution, and this is normal distribution, which is Gaussian in nature, probability distribution, Poisson distribution, binomial distribution, sampling distribution, T distribution, F distribution. I mean, there are lots of distribution that we talk about, and some of them are discrete. Okay, that Poisson distribution. I think the people have already done in first year or second year this kind of mathematics, Poisson distribution, hypergeometry, then some exponential gamma function, gamma distribution. Okay. Uh, Most of the time we don't deal with this kind of Weibull distribution. Basically, these are very special, and um, mainly people talk about this normal distributions. Okay. Uh, and it becomes standard normal when it that one it is taken. Okay. Now uh, you can see I am moving this. Okay, can you see my car? I mean this pointer. Hello.
Yes, sir. Yes, sir. It is
Okay.
feasible.
Yeah. This laser pointer. Okay. So this continuous probability distribution is that when the random variable of interest can take any value in an interval, it is called continuous random variable. Okay. And every continuous random variable has an infinite, unaccountable number of possible values. That is any value in that interval. See, in general, what you mean that uh, if we say it is discrete, that means we always think that it is only one value. Okay, so uh, that's why it says that continuous random variable differs from the discrete random variable. So basically, that's the difference, that you have always some kind of a continuous value. So if I plot fx with the how it varies with the x, so you will get a continuous curve, just like if I show like this thing. See, it is a continuous curve, it's not just like one curve. Okay, earlier that was here we showed that it is somewhere we are showing that it is just only one point one here. It's not like that. But here it is this, see, you see that it is continuous. So that's the difference between the discrete distribution and the discrete distribution and the continuous distribution. So this normal distribution is always a continuous distribution, and under that category, this gamma distribution, exponential distribution, all these things come, chi square. And whereas this Poisson distribution, binomial, these are discrete. Okay, so you get a single value. Okay, now see, uh, now what is the use of this probability distribution? Okay, distribution of a discrete or continuous function is widely used in simulation studies. A simulation study uses a computer to simulate a real phenomenon or process as closely as possible. I mean, what kind of real phenomenon? If all these things look very abstract until and unless we give some example. If you recall, I was talking about the introduction of a new drug or a medicine. Okay. And see, the same thing I have noticed here, it has been given a study involving testing the effectiveness of a new drug. The number of the cured patients among all the patients who use such a drug approximately follows in binomial distribution. Now, all these things have been done. Say, introduction of a new drug or medicine is not an easy joke. First, you have to, uh, uh, some people have to be put on trial, and maybe most of the time it is given to some mouse, uh, how it works, okay, how the mouse are behaving. Then you put it to some cattle, some I mean, cattle means some cows and all these things, and then you see the behavior, and then ultimately it is put on the human being. So there are several stages to find this thing, and it has been found that it is binomial distribution. uh, Once all these stages or steps, whatever it is, that is it becomes successful, then only you can introduce the new drug or the new medicine. Just like you might have come across the people are trying their best throughout the world just now to how to fight coronavirus, and for that there is some trial. Oxford university is trying, there are other universities. So if you go back, you will see like that they are also trying some I mean, some people are they are voluntarily going for this, taking this kind of medicine trial. Okay, so it's not an easy joke. So uh, you never know what is going to be the outcome. It can be positive or it can be negative. So uh, but all of these things, okay. So why do we do this thing? Also, this probably all these distribution functions, that the use of simulation studies can often eliminate the need of costly experiments, and is also often used to study problems where actual experimentation is impossible. See, we cannot try with each and everybody. You cannot put the life of each person, or you cannot put the a life of let's say of this total area, maybe this city, into at stake. So you have to just take some people for trial, and you try with them, and if it becomes successful, okay, fine, then you can become very uh, you can be sure. So it eliminates the need of the costly experiment. Okay. Otherwise, who is going to give the compensation? So if the people die or something happens, or let's say it is in other kind of experiments where it is a lot of expenditure is involved. So that's one of the thing, and it is the benefit that we use. And also in ticketing system in airport, the arrival of the passenger can be simulated using Poisson's distribution. So it has been found by application of this kind of distribution. Okay, fine, they follow it. So that's why. Okay. Now, how probability and statistics is, they are interlinked. Okay. Probability is the chance of an outcome in an experiment. Okay. You all of you know this thing that it is called event, and just as I said, that tossing a fair coin, and how come can be head or tail. So how many times the head can be, so you say probability is half. Here also, if I say what is the probability that tail will come, it is half, because there are only two outcomes. Okay, so it is, so probability deals with predicting the likelihood of the future events. So you are just predicting. Okay, uh, just like some astrologer or something like that. Similarly, okay, statistics involves the analysis of the frequency of the past event which has already happened. You have those data. Okay, so you are just analyzing this frequency, how many times that happened, how many people have taken this test and all these things. Anyway, okay, so also here it is, just here it is future events. Only thing here it is past events. That's the only, okay. Now, if I say that there is a drawer which has got 100 socks, 30 red, uh, 20 blue and 50 socks, so there can be a different distribution. Okay, I can just okay, mix them or all these things. We can use probability to answer question about the selection of the random sample of these socks. So yeah, it can be that what is the probability that we draw two blue socks or two red socks from the drawer. I pick up only two socks, and that all two of them are blue, or all these two are red. Okay, or if I have three socks, okay, are having the matching pair, what is the probability that we draw five socks and they all of them are black? So that can be a lot of permutation combinations. Okay, so probability actually deals, or I can also say, okay, fine, statistics already has got this. Okay, this has already was there and all these things. So probability in one case, it gives the what would be, that means the future things. And I also know from here that already this thing has already been there, so it is the past event. So that's the way they are interlinked. Okay. Now, a probability distribution is the definition of probabilities of the values of the random variable. Okay, just given that point two is the probability that a person in the ages between 17 and 35 has had childhood measles. Okay, you people might not have measles when we are very much kid. At that time, measles was almost close to the smallpox and all those things. Okay, in our country also measles happened. Now it's not there. In India, you don't expect the measles. Now, what is the probability that, okay, that if I if I just let's say that it can be probability is 0.64, 0.32, 0.04. Okay. Now, uh, it can be in data analytics, the probability distribution is important, with which how many statistics making inferences about population can be derived. So in general, probability distribution function that looks like that. Yeah. Okay, so it is fx is equal to px. So fx is here, that okay, fine, that it can be 0.64, 0.32, 0.04. So we saw like this measles studies. Now, again, as we said already, that normal distribution function that is symmetrical, mean, mode, and median are all the same, and the total area under the curve is 1. We already described this thing. Now, why we say the term continuous probability density function? Now, the curve describe the probability of getting any range of values. Okay. If I want to say that, okay, what would be the probability x greater than value 120, or x less than 100, or what is the probability in between 110 and 100? 20. So basically, the area under the curve is probability, and area under the whole curve is 1. So if you look into the curve, normal distribution curve, okay, that Gaussian curve, the whole area is 1, which is extended from minus infinity to plus infinity. Okay. And for a specific number is okay 0. Okay, we can have this thing also, that can value also possible. Now you have to look into the example. Let's say here is just IQ value. Okay, intelligence quotient has been shown in an interval 20. So what is the maximum IQ value that human being can have? Any idea? Hello, any idea what can be the maximum value of IQ? Can you hear me?
Yes, sir.
Any idea what can be the value of IQ?
No, sir. 130.
Well, some people say it can be 140. Some people say 100. Okay,
160.
160. Okay, uh, but I don't know where they exist and all these things. Okay, so that is also uh, another I mean, it is also a question where they exist and who they are. So maybe that the density, that distribution has been shown something like that, that okay, fine, uh, in one, let's say in one area, that okay, here these people having this IQ value in between 95 and 115, okay, their density is this much, point is 0.001. Okay, or in some place it's like something like that. Okay, so that's the way it has been plotted. Okay, now if we decrease the interval size, okay, and we can see that here, okay, that it is showing some plot, okay, some distribution, something like that. Okay, earlier it was, you can see that okay, fine, this interval were more, and distributions were almost, they are close to here. Here it is a sudden drop. Okay, here it is a very low value, here also very low value. But once you make this interval size smaller and smaller, okay, then you can see the curve is I mean, that values are these density values are something like that. So if you just connect them, okay, their peak, it tries to take a shape which becomes a normal curve, okay, normal Gaussian curve. Okay, it follows this thing. Okay, so it is just it is just like the definition of your just like limit. Okay, if you just make delta x as small as possible, okay, then that's the way you define that dy dx. Well, similar to that, if you just make all this, okay, this interval smaller and smaller, so eventually they will become something a smooth curve, okay, continuous curve, which will give you this kind of normal curve. Now, as I said also that a special kind of continuous PDF, okay, normal, that mean value, okay, mean and standard deviation, and because of the variation of the standard deviation, the spread can be higher, and if your standard deviation is higher, the spread is more, and here's this spread is less, so it is that it is steeper curve. So if I say that grade, just like okay, it can be seen also for the number of the students. If I plot the grades and the student density, that how many students are there, it can always be followed that this is like okay, this is very narrow here, and this is wide here. Okay, so undoubtedly most, as we said that earlier also, that for a random variable, normal distribution we follow, that's Gaussian distribution. Now, recall continuous random variable are described with probability density function. Normal PTF are recognized by their typical bell-shaped curve. We talked about this thing last time also. And area under this curve is equal to 1. Okay, and also we know that this side is 2.5, this side is 2.5. Okay, we also talked about this inflection point on this side. In between that is only we gave this example also, that male height normally with the mean value this and standard deviation this. Okay, 68% falls within mu plus sigma, and then 32% in tails, 67.2 and 72.8. Okay. We already talked about this thing, that we talked that 68% between mu minus sigma, mu plus sigma, and this is also 95% mu minus 2 sigma, mu plus 2 sigma, and this is within 99%. Okay, so basically these are all it has been found that these are the probabilities associated with the normal distribution. Okay, now a normal and when it is called standard, the difference between the normal distribution and the okay that a normal random variable, when this mu value becomes zero, that means mean value is zero, and sigma square or standard deviation is one, or the variance is one, it is called standard normal. Okay, variable, and a standard normal variable is denoted by Z. Okay, we already talked about Z score. So, and the value of the function, okay, it is nothing but probability less than Z, is used to denote a probability. And there are always some table at the back side. Here it is appendix A. It is called cumulative distribution function. Okay, a table or a computer software is required because the probability cannot be determined by eliminatory method. So you will be always given a table. Okay, so let's say you have been given this kind of table. Okay, there you will see that this is Z value, and on this side this. Okay, so if anybody says what is the probability of 1.5, that means this is the area. Okay, below this. Okay, so if anybody says 1.5, that means this is below this Z value. Less than or equal to 1.5 means that on the left hand side area under this curve, and as because it is 1.5, so you have to just search from here. Okay, and if it says that okay fine 1.51, then you have to go to this side, and then you have to search this value, and then you have to pinpoint this one. So basically, in your exam or anywhere, if it is asked, then accordingly you have to search, and you have to find out the value like that. Okay. So how do we get? So any kind of norm. Okay. If a problem is given, just you see. Okay, and then you find you subtract this mean value divided by the standard deviation, and then you come up with the Z value, and this Z is called the normal random variable. Okay, as I said that any okay, uh, if you want to get the value, okay, Z less than Z, okay, you will get the probability value. So what you need to do is basically you have to search for that value from the table. So it becomes more clear once you look into the table. Just here one example. Okay, if you discuss this example, then it becomes more clear. Now, let's say one in a machining shop, one shaft has been given, and the diameter in an optical storage drive is normally distributed with the mean value 0.25 0.08 each, and standard deviation is 0.005 inch. Okay, so although okay, the machining can be perfect, but there is always a probability that there will be some deviation, some has something. Okay, machining thing. Okay, the specification on the shaft are 0.5 to 2500 plus minus tolerance. So it is 0.005 inch. What proportion of shaft conforms to this specification? Let's say X denote the shaft diameter in inches, and uh, if you just add this one, okay, in plus side it will be 0.2515. That means you add up this value with this, and on the negative lower side you have to subtract off, and then you come up with 0.2485. So you have to pick up the value, okay, in between that probability. So once you do that, okay, it's like it will be, let's say it is 0.2515, and this is less than 0.24. So you have to find the value in between these two areas, okay, that these two, okay, so that's what it has been done here. Okay, that it is 0.25 and 0.2485. And once you do that, as I said, that you have to standardize, okay, z score value. So it is x minus x bar. So it is, this is x, and your x bar is the mean value, okay, divided by the sigma standard deviation. You put the value there. So ultimately this is, one is z1 and another is z2. So you have to take, oh, okay, now this is what, this is in between this. So you have to pick up this z value and look into the probability, okay, the area, and it is another area. So if you just subtract one from the another, then you get this thing. So you'll be able to say that, okay, that means here it says 91.92% conforms this specification. So that's the way it is done. Yeah. As I said, that okay, this is 0.2515, and let's say this is 0.2485. So it is just nothing, but you are just subtracting of one from the another. Okay. So similarly, you can solve this thing, this kind of problem anywhere if it is asked to you. Okay. So in case of any kind of problem that is given to you, okay, when the values don't fall directly on sigma landmark, so what you have to state the problem and standardize the values. That means you have to tell z score. By the way, how many students are there today?
25.
Hello. 25. Okay, so sketch level and set the curve. Okay. And then you will search from the table and see uh, whether you get that one. So for continuous random variable, we assign the probability to intervals. So that is, as I said, that you can get the area of the curve under in between A and B. We already solved this problem just right now. We showed this thing for the case of shaft. Okay, so if anybody says that, okay, fine, you have to check what is the probability that it falls in between this probability and this probability, then you should be able to calculate it. By the way, non-kisser is there?
Yes, sir.
You are there? Okay.
Yes, sir.
How many years, sir? Only 1 year, sir, is required.
Yes, sir. I'm none.
Okay. So you had some problem that you had been mentioning. Okay. So did you get it solved? That you said that you could not get time, this, that for. Okay. So in your last quiz, did you get the time?
Yes, sir. Yes.
Hmm? Okay. Um, Okay, so we already talked about this thing. This Bayes is symmetric about the mean of the random variable. Standard deviation of the random variable affects. So if your standard deviation is more, that means the Bell shaped curve will be spreaded. Okay, and the larger the standard deviation, it will be more spreaded. Okay, so state the problem, standardize, same thing. If I want to see that how many percentage of the student less than 65, so I have to say that, okay, X is equal to number of students with the height 65 inch, then I have to check PR X less than 65 inches, like that. And I have to normalize the Z value. Okay, so and then I have to search in the table. Okay. Now, table is a series of column containing number for Z and PZ. The Z represent the Z value for a normal distribution, and PZ represent the area under the normal curve. Okay. So, as I was saying that, okay, fine. If you just search anywhere, you will look into the back of your book or any probability book or your undergraduate book. This is the Z value. Okay. And on this side, this is okay. So if anybody says that 1.96, as I was saying now, so you have to go and search 1.9 up to this, it's all right. But you have to get another 0.06, so that 0.06 will come from here. Okay. So if anybody says that what is 1.25, so I have to go this way. And this is another 0.05. So I will be, so this 0.9115. Okay. So as I said that here it is 1.96. So this value is 1.96 here. So, okay. So anything that is to the left, okay, that it is up to this value. So that value will be given by this one. Okay, so P of 1.96 will be this one 0.97 value. So this has already been, I mean, tabulated, prepared long time back. So already we talked. Okay. So here also another example that it is shown that 0.5, if anybody doesn't say anything about what is the second decimal position, so you have to stop here 0.500, so 0.6915. So here you just look, okay, that, okay, 0.5, and then, okay, whatever the value you get, anything that is the area under this curve on this left side. A represents the lower boundary. So if I have to get in between these two values, okay, so enclose this value. So what I need to do is basically I have to search for this, okay, at this point and at this point, and then I subtract off, because if I subtract this value from this, then I'll be only left with this much. It's just like in any integration you have, when you had to get the concept of integration, you learned that, okay, integration is nothing but the area under the curve. So say that is area is equal to fx dx integration, the limit is a to b, and then again you said, okay, fine, if it is I mean it is definite integral, a to b means that it is a b and minus a to that. Okay, so you have to just take up to this value, and then again you have to subtract. So if you subtract one from the another, then you are just left with only this, okay, dark portion. So that's the way you have to, in numerical problem, you have to come up with this. Here also same thing, it has been shown that it's sometimes it is very much you have to search, which is very much painful. Okay. uh, just like as I said, if we are looking for minus 2.84, see there are also some values, negative values, uh, and we go across and until we get 0.04. So up to minus 2.800, it's all right. But this second decimal point means that I have to go another 0.04. So that's why, see, I have to go this way and search from here. Okay, this is the junction point. So it is 0.0023. So the value is area left of 2.84 is on the left hand side, it would be 0.0023. Again, we talked about this thing earlier also, that how it looks like that. Okay, this is the normal distribution curve. This is a bell shaped curve with different centers and spreads depending on mu and sigma. So if if you just change the value of this mu and sigma, you will get I mean bell shaped curve. Only thing that it will be okay. So your either the center position will be different, and also the spread would be different, but all of them are look alike. huh, okay, and you can just represent similar to this. And here this pi value is 3.14159, and E is, as you know, that it is 2.718. Okay, as I said, that these are just okay. I was just talking to you that this is indefinite integral. It is a to b integration fx dx. So similar to that, it is here. This properties of the probability density function. It's just you subtract one from the another. You just take the probability. That means it is all the way up to here, and probability of a will be up to here. So if you just subtract one value from the another, you will be left with only this okay, line values, this dark portions. Okay, and okay, sigma square is nothing, just it's x minus mu whole square fx dx. Okay, so uh, there are a lot of I mean this kind of I mean, derivations are there. If you wish, you can derive, but I don't want you to go into that kind of difficulty situations. Okay. Uh, Similar to that, there are also some, okay, some kind of definition, but the random, you just only remember that that curve is symmetrical about the vertical axis through the mean mu, and it can take any value in between minus sigma to plus sigma, although they look as if that it has reached or it has met here, but it is not such like that. It is that it is assumed that it is going to meet at minus infinity or plus infinity. Okay, so that's why the limit that is always given, that it is minus infinity to plus infinity. Okay, and fx dx, the limit is minus infinity to plus infinity, and it is 1. Okay, so you just keep in mind all these things. It's not that it is not your first year or second year derivation, or that all this identities like that. Okay, and we talked all these things earlier also, that how you can derive. Okay. So only thing that you have to just standardize these values. Okay. So same thing. It's very nicely. It has been shown that although the x value can be 50, right? But because of this sigma value 10, once I standardize this thing, okay, and mean value is that they are okay, uh, and we can easily, okay, x here is 50. Okay, so it will be just 0, -1, -2, -3. So the z value is varying in between -3 to +3. Okay. That looks nice, and you feel it would be convenient. Whereas x value here, it is just 20 to 80. Okay. Sometimes it may become very inconvenient to handle. Hmm. Then all these things, it's a standardized value of x is equal to z, x minus mu. Okay, and you can also, once you put the value of z is equal to this, you can convert fx dx as this one. Okay, minus 1 by I mean it is 1 by root over twice pi e to the power minus z square by 2. Okay, so you put this value z into that previous equation, just like here. If you just put the value of this one as z, okay, certainly you are going to get a, then you come up with this value. Now, here is one example in which it shows that height in inches of a random sample of 52-year-old males. That means there are kids whose age is 2 years and their number is 50. Okay, and create a relative frequency distribution with the lower class limit of first class equal to 31.5 and a class width of 1. Okay, so, and you have to say that this variable is whether it is normally distributed or not. So basically, their data is given here. That how it okay, that is actually distributed. Frequency, okay, that it is given there. Okay. So once you plot that, because of from this data, you can have a histogram. Okay, and with the frequency, their height is here, and this percentage. How many percent of the kids, 2-year kids, they fall in between this height, 32.5 and 33.5, in between 35.5, 36.5. So that distribution is something like this thing, and here also you can look that the it looks like a just like a normal Gaussian curve. Okay, so it comes in the shape of a normal Gaussian curve. So even I mean this data has been given in such a way. Okay, um, or it happens also in real life that you reach a normal Gaussian curve. Okay. Uh, and how does the area of the rectangle corresponding to a height between 34.5 and 35.5 inches relate to the area under the curve between these two heights? So the question that is that in between 34.5 and 35.5, okay, it is this. Okay, and how that curve, okay, that how does the area of the rectangle corresponding to this thing, to a height, relate to the area under the curve? That means, okay, you get one area here, and what is that part? Okay, what is the percentage of the fraction of the total area? Okay, if you take this thing as one, or so here it is plotted something like this thing, normal curve. Okay, and as I said, that only you have to that has been highlighted here as the green curve. Okay, so you just need to find how much that area has occupied. Okay, with respect to the total area. Okay, what fraction you can say? It's better to say. Okay, so that's what the histogram of the. So what in this kind of problem, what you need to do is basically you have to have one histogram from all this data that is given to you. For that, you have to just distribute and you have to decide how much interval that you want to have. Then you plot this thing. Okay, and from the curve, okay, so you can have it. I mean, again, you have to search it. Basically, what you need to do is you have to take this thing and standardize it. Okay, z minus as I said that z is equal to x minus x bar divided by okay, sigma. So you have to find out the standard deviation, also the mean values. Okay, and from there, okay, you just convert these values into the values of the z. So z is how you vary it. from my, let's say, -2 to minus +2, and then you calculate this value. Okay, then you first you calculate up to here, okay, and then up to here, then you probability of this minus this, that would give you how much is that percentage and all those things that it would be coming up of this whole area. So let's say it is another interpretation of the area under the curve, normal curve. The weights of the pennies minted after 1982. Pennies is nothing, just just 1 cent. Okay, in England it is pennies. In USA also pennies. It's just like 1 paisa. We don't use anymore 1 paisa. You people didn't see, but I saw that now it doesn't have any value. Even 1 rupee doesn't have. That is the devaluation of our currency. So they have it has got high value, and during the year 1982, and the weight are normally distributed with mean 2.46 gram and standard deviation 0.02. Although it is a metallic, but anything that is minted, there can be some variation. Okay, it's not necessarily that it has to be sacrosanct, that it is to be perfectly 2.46. So that's why it is said that mean is 2.46, but standard deviation is 0.02. So it is said normal curve parameter set the region under the normal curve between 2.44 and 2.49. That means you have to just in between two okay line, you have to set this thing, and region under the normal curve. Okay, suppose the area under the normal curve is 0.7745. Provide two interpretation for this area. That means we have to say, okay, fine, that up to this, okay, up to this value, I have one, okay, probability, and up to this was one probability for this z value. Okay. So it is shown here, okay, that it is a, it has been right, that mu value is 2.46. Okay, that mean value is 2.46 and sigma is equal to 0.02. So in this kind of function, it is like this, and once you plot it, okay, fine, you are somewhere here 2.46, and you have to get in between 2.44 and 2.49. So you have to somewhere in between here and here. Okay, so first you have to get this up to, okay, and then again up to here. Then if you just subtract one from the another, okay, so that you can get also all these things. Okay. So it is just another problem. Find the z score such that area to the right of the z score is this much. So anything that is 0.3021. So if you just subtract, okay, one from the another, okay, this value, one minus this value, it is giving you 0.6979. Okay, so you just if you plot it, and then you will see on the right hand side it is 0.3021. So if you just on the left hand side, it will be 0.6972. And then again, what you have to do is you have to just go into a curve. Okay, you have to look into table. Okay, just like we are searching for table in another cases. Where did we search? Uh, some cases, okay. So similar to that, you have to just search where you are getting. So what is the value of the z? Okay, so you have to search that where that value is, and then you have to get the value of z. Similar to that, here also, you have to search from the table. You have to, and you will get the value of z is 0.52. So basically, it is nothing but play with the table. So how much you are efficient and how much you are able to catch up the problem. So, uh, as I said, okay, it's just a summary almost. You can say that in when Z value in between A and B, then it gives the probability of the standard normal variation. Okay, and Z greater than A means that anything that is beyond A. So anything on the right hand side. Okay, if you plot a curve, okay, normal curve, then anything that is on the right hand side, okay, and always remember on the right hand side that or anything greater than A, it would be listed this, and if it is less than A, that means on the left hand side. Okay, so represent the probability of the standard normal random variable less than A. So here it is shown something like that P is equal to minus Z minus 2. So it is on the left hand side. Okay, anything. So if you have here 0 and the Z value is varying in between minus, it has already been normalized. Okay, the standardized, not normalized, standardized value, and it is minus 4 to plus 4, mu is equal to 0, sigma square is equal to 1. That Z below, okay, below minus 2 is only this area, and it has been found that it is okay. You have to go to the table and you would find that it is 0.0228. So that is one use. It shows how the area below this. Similarly, okay, here is also another one, minus 1. Similarly, if anybody says that, okay, if it is greater than 2, then you have to um, find this value, okay, here, that, okay, how it looks like. Okay, that first you have to get up to the here, then 1 minus, okay, then only you can get this, only this left out portion. Okay, that's what I was saying, that okay, that area below Z, okay, that this area point, because if you search from the table, you will see that PZ, okay, PZ is equal to 2, maybe it is 0.97. So 1 minus 0.97, that would give you 0.02. So you'll get only this area. Otherwise, total area is 1. Okay. So that's in general, this kind of problem will exist. Okay, so that much I wanted to say today, and I'll give you some link through your Google Class room, and over there also you will find you work out, and maybe next to next we'll be having some quiz on this. Okay, all right. So if you have any question, please let me know. Otherwise, we'll stop here. No question? Hello?
No, sir.
Okay, all right. Okay, then thank you. Good night.